Okay. Okay, today we are glad to have Dr. Harold Kirkham as a speaker of today's seminar. So he obtained his bachelor and master degree from Austin University in the UK and his PhD from Drexel University in Philadelphia, Pennsylvania. Then he has worked mainly on measurements in the power systems at American Electric Power. He was responsible for data system at the ultra high voltage research station in Indiana. After that, he worked at NASA's Jet Propulsion Laboratory in Pasadena, California, where he managed a DOE project researching measurement and communication for power grid. From 2009 till 2021, he was at the PNNL, and he is active in IEEE and Instrumentation and Measurement Society. And he is a chair of a working group revising a standard for 1459, the standard that defines the measurement of power and reactive power. He's almost finishing his book, which is co-authored with collaborator from New Zealand, Germany, England, Ireland, and the US, which will be published by Wiley soon. Its title is Measuring the Grid, the Mysterious Explained. A very mysterious title, so we are looking forward to that book. Okay, thank you, Harold. Back to you. Floor is yours.
Thanks, Syed. You've got to explore some of the mysteries today. There's a thing called power theories. I'm curious whether people have heard of power theories in this group, but they're a mysterious thing and invented by power engineers. And we're going to be demolishing them all in a few minutes. Next slide, I should say, but just press a button. There are various ways to do what is called metrology, which is the art and science of measurement. And there are different kinds of measurement that we make. And we're now going to understand why there's a problem with reactive power unless we appreciate the two kinds of measurement. Next. And the reactive power problem is exposed in part 4 in sort of more detail than you might think is appropriate, but we need to understand why it's a problem. And the next slide, the next button rather, will end this thing. We should, of course, we talk about the solution, and the solution is in that new standard 1459. Next, we should get a new slide. This is my view of human evolution. It starts on the left with Homo sapiens, and somewhere around 500 before the current era, working man split away from natural philosophers. They ultimately went extinct, but not before they had split into physicists and electricians. And you see university man over there splitting up from physicist. And the Latin subtitles might interest you if you know some Latin. But there we are. And in November 1894, a paper was written that separated overnight the electrician's world from that of the natural philosophers. And the paper was written by a university professor and one of his students, and he was also a manufacturer of measuring instruments. And what he had introduced was the solution of a very aged problem solved by using direct reading instruments. And the world of science didn't think we should use direct reading instruments. Imagine. Next. Yeah, that's the citation. I'll have all the citations available if anyone wants them later. One of the problems we suffer is that there are about 30,000 members in the IEEE Power and Energy Society, and only a tenth of that number in the Instrumentation and Measurement Society. So we don't get enough attention paid to our measurements. How many people overlap? Hit the next button and we'll see. it is 365. So something very small, a right arm of a person is involved in both measurements and PES. That's not enough. That's considerably not enough. So we get these power theories. There's a power theory for you. You might have come across this foam on the beer nonsense as a power theory. I drew that. That's SRM, stands for standard resource material. Anyway, next slide. Real power theories, which defined, the first definition I could find for power theory was in 2008 by these guys, and their definition is fine. Power theory is what you do when you're trying to find an answer to why P is smaller than S. And a similar definition was given later, next slide, by Leszek Sarnecki, who said, essentially, this is the central problem of a power theory. And he's right, it is. If you're going to have a power theory, that's what you've got to solve. Next. And this comes from Louisiana State, which is where Sarnecki works, and he's written a book giving his latest power theory. But he says that in the 20th century, there were 9 different power theories. I can believe it. He studied this a long time. Next. However, he thinks now he's got the answer. He's proved all existing power theories were erroneous. And now he's got the only correct power theory of electrical systems. There are sound effects on this. I hope you hear them. Go with the next button. There you go. There's supposed to be a buzzer noise. This is actually quite nonsensical because I'm going to show all power theories are wrong, including his. Next. Here's some of the perpetrators. William Hand Brown, working at the time, Illinois, University of Illinois, gave us the name Reactive Power in a letter to the editor of a trade journal in the end of 1901, December 1901. So we have him to blame. Next. Konstantin Budanov, some of you may have heard of him, wrote a book in French, published in 1927, in which he introduced something called distortion power as a way of explaining the fact that the power triangle, which really came into use about 1910, was no longer working. Next. Stanislav Frese wrote in German and Polish, so you're kind of stuck if you don't speak either of those. There hasn't been any really widespread translations of either of them, but he invented his own power theory to explain why power was smaller than apparent power. And Manfred Deppenbrock wrote also in English in 1962. So it's an ongoing thing, and FBD stands for Frese, Buchholz, and Deppenbrock. He wanted to get some help doing this. And the picture there is a picture, a privately held picture, shall we say. And this is a public picture of Leszek Sarnecki, who's the only one of these people still alive. And he invented his CPC, which you can think of as Sarnecki's power concept, in 2008. Next. And yeah, he thinks it's the currently most valid thing, but it isn't. So he wrote a paradox, and his picture of the paradox, if you take a power source that has some fundamental and some third harmonic, and you inject that into a load that consists only of an inductor and a capacitor, you can fiddle with the values in such a way as to make the apparent power at the reactive power at the third harmonic and the reactive power at the fundamental equal and opposite, because you've got an inductor and a capacitor, and one tends to absorb and one tends to generate reactive power. So you then have a paradox that at the load terminals, there is a current flowing, there is a voltage applied, and yet your total measured reactive power is 0. Now, he never explained that. We're going to see an explanation soon. Next. Yes, go on. The explanation for why this is all nonsense is simple. There's a logical fallacy. And just in case you don't know the logic symbols, and frankly, I didn't until I had to help one of my kids through this class in high school. There is a thing called negation, the tilde, that means not. There's a sort of a staple on its side implying implies or if then. And so we write P standing for the proposition that power and apparent power are equal, and an angle, the proposition that there's an angle. So next, you wrote down P, and then the rest of those symbols will be if the apparent power equals power, then it is not the case that there's an angle. True statement. If the power and the apparent power are the same, there is no angle, on the assumption that everything is describable by a sine wave. Next, with those as a reminder, this idea became entrenched, and power P, and then the staple symbol tilde and the angle naturally led to its opposite, which we read. If it is not the case that power equals apparent power, then there is an angle. Next, and a Steinmetz paper in 1892 showed experimentally that this was not correct. And it turns out that it's understandable why, because if you replace Q, angle with a Q, it's the same statement. If it is not the case that power and apparent power are the same, then there is reactive power. Next, that's what that would read. Next is also wrong, just the same as with angle. Next, all power theories are invalid. The existence of a difference between S and P cannot be blamed on any particular cause. And the point of it all is that there's a hidden assumption if you assume it's reactive power. It could be nonlinearity, it could be hysteresis, it could be time variation of load. The fallacy is ancient. It is known in history as the denial of the antecedent. The first part of that proposal is the antecedent. And if you deny the antecedent by putting the not in front of it, you invalidate the statement. You don't make a not. It's not like Boolean logic. So why are people making this mistake? Because they don't understand measurement and they want to look for a solution that doesn't involve measurement. They want to think it's a power problem. Next. So we're not going to do that. We're going to look at metrology. There are three kinds. Scientific. We all expect to make scientific measurements. Turns out it's not what we always get. Next. This guy, John Simpson, and to my mind, that is a face full of character. I never met the guy. I wish I had. He wrote this excellent paper in 1981 that describes the various kinds of metrology that there are. It includes scientific, commercial, and the next one, which is legal. Legal metrology, hit the button again. Legal metrology is what you get when the measurement has to comply with the law or regulations. This is what's involved in measuring for the purpose of sending somebody a bill. And it turns out, very strangely, that the idea of metering and billing takes you out of the world of science. What you have to do is make a measurement that can be repeated, can be understood, and will be consistent. So you don't do scientific measurements. This picture of the car, this is a Citroën 2CV, and that stands for 2 chevaux vapeur. And that means 2 horsepower in French of the time that this car issued. It is not a 2 horsepower car. It is a 2-horsepower car because the French authorities that wanted to tax the thing didn't want to bother measuring the actual horsepower. So they came up with a formula that said it's got so many cylinders, the stroke of the cylinders is this, the diameter of the cylinders is this, and if you put that into the right formula, that's a 1 point something or 2 point something horsepower, and we round it down to the nearest integer, which is 2. Nonsense. They got a lousy formula, but that's a legal approved measurement. Next. And what you get is this official seal of okie dokie. This passes the requirements for measurement in the legal domain. It is total nonsense in the scientific domain. Next. There's 2 kinds of measurement apply. On the left, representational measurements, on the right, operational measurements. One is largely concerned with science, the other is largely concerned with legal matters. Next. And there they are. It's not 100% separation, but close. Legal measurements are almost all operational. Representational measurements are almost always for science. Scientific measurements are to do with taking information from the world of the physical world, which Maxwell described in 1870 as a dance of molecules, and moving it to mathematics, which he described as an operation of the mind. And a few years after that, he wrote his thesis, his treatise on electricity and magnetism, which begins with the definition, a paragraph that defines what measurement is. You can get that easily on the web. And Maxwell died not long after this. So that's probably a picture of about how old he ever grew, believe it or not. Next. I put it down as a bridge right in the middle, an isomorphic bridge. Isomorphic meaning it's reversible. You can go from the physical colored world on the left to the dry, abstract black and white world on the right via a scientific measurement, via a representational measurement. Tells you what something is, tells you what it means. And in the power system, remember this, there's only 2 observables, the voltage and the current. And all these other things we make up are based on that. The representational measurement is based on a measurement model. It's an equation, and it describes the interaction between the physical quantities involved. And if it's direct, there's only one parameter. Indirect has more than one. And all of these things are necessary to keep in your mind because you're juggling a lot of things that are in the end going to come together. So you maybe don't have to remember all the detail at this point, but you come to the end and be reminded of them all. Next. An example of a representational measurement. There actually aren't that many. Shear stress inside a beam, you can measure by inferring it from the strain, which is the deflection. And it's a simple calculation. Similar for density, you measure the mass and the volume, and you make a very simple calculation. For AC voltage, that's a measurement model. It's time dependent, and you have to express in the rules of measurement, you have to express the time dependency, because there's a requirement in measurement theory that when you make a measurement, all the parameters in the measurement, which in this case is V hat, omega, and phi, have to be constant throughout your measurement. You cannot measure these things if they are changing. You must account for the rate of change of their measurement. So there's how we account for it in voltage. And of course, the same in current. An operational measurement is one way. It's not isomorphic. It's the other thing. It will take you from the world of the colored physical world, and it will take you into the abstract black and white world, but it will do it in a way that doesn't let you know how you got where you are. An earlier one was the development by Brinell in Sweden of a way to measure metal hardness. And in 1914, 2 unrelated people, both called Rockwell, both working for the same company, used a different indenter and different forces and came up with the Rockwell method of measuring hardness. And Vickers, a little bit later, developed their own method of measuring hardness in England. And all these methods are still in use, and they don't give you the same number. So when you say what you've measured, you have to give how you measured it as part of the description of what you did and what the result is. Next. Operational measurements these days are laid at the feet of a guy called Bridgman. Bridgman was a Nobel Prize winning physicist, and he wrote a book in 1927 that, hang on a second, I've got to do something on my other screen. Just a moment. I don't want that view. That's what I want. Okay. He wrote this book to explain something about what Einstein had done. Einstein had come into the world and caught physics unaware. And what I was looking up was the quote from Bridgman. What he said in his book was, it was perhaps inexcusable that a revolution in mental attitude should occur once, because after all, physics is a young science and physicists have been very busy. But it would certainly be a reproach if such a revolution should ever prove necessary again. And so he wrote this book explaining why measurements and why the sort of thing that Einstein did depends on how you make these measurements were in fact operational. And he comes out with this quote, which is hard to understand. I think the concept is synonymous with the corresponding set of operations, but you have to let that sink in before its full meaning is evident. But Percy Bridgman is usually tagged with being responsible for operationalism. Next, here are some operational measurements. The most clear and obvious one is octane in the US, which is disclosed by a little yellow sticker on the pump. And if you ever got nothing else to do and you stare at the pump and you see R plus M over 2, what does that mean? Well, it means it's what you're seeing as 87 is the average of R and M. Yes, but what is R and M? And the answer is they are research and motor. And what that means is there are two kinds of gasoline engine that you can get for this test. One is called research, one is called motor. The research engine allows you to detect knocking while you adjust, believe it or not, the compression ratio of the engine. The motor method allows you to adjust the ignition timing. Most of the world uses R. The US decided to use the average of R and M, and that's what 87 gets you. And the number is a percentage. It's the percentage of octane in a mixture of octane and heptane that gives you knocking at exactly the same point on the scale that your test fuel does. And that's the characteristic of an operational measurement. You have to specify exactly which engine, what oil pressure, what speed is the engine running at, what temperature is at. All of these things are carefully controlled. And the same is true with all of these other operational examples down here. There's not only metal hardness, there's a test for rubber hardness. Shaw A72 is about the hardness of a car tire. If you're interested in partial discharge, you'd look at IEC 60270 because that's the only thing these days that governs the measurement. Anything with RMS in it is bound to be an operational measurement because the root mean square is an operation that can only be carried out exactly as described. And reactive power has been unrecognized as an operational measurement and is a major problem. Next, how do we differentiate between operational and representational? Sometimes it's not easy. So I put this table together. It's hard sometimes to distinguish a clear and conceptual distinction. So if you skip to the end, it's generally possible with an operational measurement to have a long and entirely fruitless discussion over the meaning of the measurement. And that's the obvious way, and it's absolutely a good distinguisher between the two. But on the way there, example 2, can you change the method? In an operational thing, you cannot. In a representational one, of course you can. Can you improve it over time? And it's the same answer, not if it's operational, but yes, if it's representational. Are measurements one-to-one? Do you always get one answer? Well, yes, from a scientific measurement, a representational measurement, not from an operational one, and so on. And I'll let you look at that in your own time later if you want. Next. Now we come to reactive power. NEMA, the National Electrical Manufacturers Association, published this document, technical report C12.24, in 2010, and an updated edition in 22. And they defined several ways to measure reactive power. That's what their title was. It's on the bottom, definition for calculations. And their number 3.1 is multiply the volts and the amps and the sine of the angle between the sine waves that represent them. Okay, next. These are the others that they looked at. They actually didn't really look at 3.1, but they did look at the ones we've numbered 1 through 10. And for example, number 5, delay the voltage samples by a quarter of a period. Well, okay, you can do that in a digital world. It used to be done by integration and differentiation in the analog world. Number 10, if you look at phase A for the current and phase B and C for the voltage, if everything's balanced, those will be at right angles, and you do a multiplication and you don't get power, you get reactive power. Well, that's the theory. So there's all these methods of making the measurement. Now, not only does NEMA do the work and do the test and test all of these things, they present the answers. They even present the breakdown as to what the frequency, the fundamental frequency is. Next slide. Okay, here's what you get for 9 or 10 methods and going across 14 different waveforms. Now, the first 2 waveforms, voltage and current, both described by sine waves in phase. All the answers come out with 0, including the fundamental. Fine. Shift the thing 90 degrees. All the answers come out at 900, in this case, kVA, I think. And except for one that can't make up his mind and describes it as, oh, no, that was negative. And then you get a tiny little bit of distortion on the third wave, and that causes a scatter. Some decide it's up, some decide it's down. And the red one means it's an imaginary number. I don't know how you get that. Obviously, in the implementation, they're taking the square root of a number that's negative. Why is beyond me. In the fourth one, we can see again, most of the people agreed with the fundamental, the frequency somewhere, the number somewhere just above 400, but some were higher, some were lower, and one, of course, was mistaken, plus and minus. Anyway, this is sort of silly. If you're going to measure reactive power, you should decide on a method. Are you going to let the customer choose which of these methods to use? Next, this has all been sealed with okie dokie at the moment. That's got to change. Next. This is a cartoon from my book. And I think that just covers it. This is all the good that reactive power is at the moment. Next. Why do 10 different methods get the same name? Because people don't know that you're supposed to give them their own name. That's because we don't teach any measurement theory to power engineers. Next. Now we go back to the evolution, taking a snapshot a little more recently. Okay, next. Reactive power was named, as we saw, in 1901. Next. By 30-some years later, we've got system voltages above 250,000. I think that's impressive. The next thing is measurement scales. Measurement theory separates itself from measurement man somewhere around the time of World War II, 1946 and later. And I draw it as a thin line because, frankly, there aren't many people there. So we're not, anybody that's taught power systems and is presently teaching power systems has learned it almost certainly from somebody who didn't learn any measurement theory. So what do you get? Next, you get this. Well, I maybe don't want to accuse the people at Washington State University of saying the power triangle was okay when they were kids. Why do I need measurement theory? But the answer is you need measurement theory because you don't understand what reactive power is. Next, why doesn't it work? Why is there a cottage industry developing power theories apart from the fact that nobody noticed the fallacy? Next, two important theoretical considerations, Cauchy's equation and next, concatenation. And these two are essential. Next. Cauchy is simple. If there's a continuous function, you can see it such that the sum of these is the same as the separate sum, then that's not obvious until you think about it. But it's the same as a formula y equals ax plus b, only b equals 0. And that's what it's saying, that there's no offset. You've got some sort of a natural zero in this thing. Next, and apply this to measurements. We don't use a plus, we want to use a circle. That was a notation introduced by a guy called Rudolf Carnap in a book from 1966 that said it's incorrect to put the plus sign in there because this is an operation. This is what concatenation is. It's combining two things together in the physical domain. Next, because why? Because in that formula, everything inside the parens is a physical thing and everything outside is a not physical thing. So we concatenate A and B in the physical world, and then we measure A and we measure B. We want to see a result that says the measurement of the two things concatenated is the same as their separate measurements added together in the mathematical world. So the question then that Cauchy addresses is how do we know that A concatenated with B is legal, as it were, in the physical domain? Next. Next. It works there, by the way. When I drew that, I put Cauchy's name on the thing. There's no evidence at all that Cauchy ever produced a kitchen scale. Next. So there haven't been much written about concatenation. So we've generated 4 rules in the book. It is an activity in the physical world combining two physical things possessing some property in such a way that the magnitude or property of interest of the combined thing can be measured. That seems fairly clear. And in the case of the scale, this is obviously another way of making a measurement of weight. This is a representational measurement because 2 different methods give you exactly the same result. Next, only things of the same kind are concatenated. That is obvious. What is not obvious is what does the word kind mean? Next, the result of the concatenation has to be measurable by the same method you used for measuring the separate things. Yes, you can't go changing what you use to make your measurement. And that, for what it's worth, it means that the properties have to be stationary, at least for the duration of the whole process. If necessary, the orientation or alignment of properties of entities can be changed. So you can line up 2 rulers, or you can add 2 voltages in phase by shifting their phase if you want, if that's what you want to measure. Next, of all of these, the hardest thing to understand is number 2, that is things of the same kind, but number 3 sort of helps to explain. And we'll get to what kind means in the measurement sense soon. Next. Okay. We already said everything up to the word temperature. Can't do it with temperature, even the Kelvin temperature. So while Cauchy is useful, it isn't entirely a guarantee, but it works for all the things that we are going to worry about. Next. Now, as power system guys, you know that you can take some voltage as a function of time and current as a function of time, split that into harmonics. It's a three-phase system, and at each frequency, you can give everything the Fortescue symmetrical component treatment. The end result is a whole lot of numbers. The Fourier transform and symmetrical components transform both. Back up, please. They preserve the degrees of freedom of the signal. Next. In that system there, measurement model there are 3 degrees of freedom for the fundamental, 3 degrees of freedom for the harmonic H, and 3 degrees of freedom for the harmonic K. And you can imagine that this is a 3-phase system. Next. Accounting for duplications, the degree of freedom number grows to 39 for a calculation of reactive power for that set of parameters. Turns out to be less than 54 because you don't count the frequency over and over again, particularly. But still 39, and yet people are seeking a single quantity to explain reactive power. Single quantity, 39 degrees of freedom. In order to fully understand that system and its reactive power, you'd have to make 39 separate measurements. Problems occur if the signal and the equation are not matched. That doesn't mean you can have spare signal. That corrupts the measurement. You can have a spare parameter because it always gets a value, and that screws up the measurement. And the results of the measurement are not one-to-one with what you're seeing, and that's the source of the random number effect. You have in some way concatenated all these numbers by the method of measurement. So resistor is a single frequency quantity in reactive power. No, wait a minute, I'm backing up. I've got no notes here. The reactive power is a single frequency quantity because the phase is the initial phase at each frequency, and those are separate. In a resistor, power warms the resistor regardless of frequency. That's very handy when it comes to RMS. It doesn't work for reactive power. In a motor, fundamental power will give you rotation. Harmonic power might just warm the motor. That means that harmonic power, as well as harmonic reactive, are different kinds of quantity. And you cannot concatenate reactive power, even if you can be bothered to measure it at the harmonics. You cannot. So the solution is use only the fundamental. And it's such a simple, trivial solution, it isn't a complete solution. But it's very clear that this is probably the most useful thing in the power system. And that's what standard 1459 recommends. It's so simple. Next. Yeah, next. Need to back up one. Here's the issue. This is column 4 from the random number diagram. The fundamental of that phase shifted waveform down near the bottom of the page gives you an appearance at the fundamental that there has been reactive power. Why? Because the first part of the wave has been cut, and that means the fundamental has been moved to the right, which means it's lagging. And therefore, the fundamental sine wave is lagging the fundamental sine wave at a voltage, and you will measure reactive power. And there's nothing you can do other than look at the waveforms to know that this isn't actually reactive power of the kind you think you want. It is indeed the displacement value. We often call this thing displacement power factor, displacement reactive power, but it can be caused by any of these effects: time varying, nonlinear, reactance in the load, hysteresis, anything like that. So it's still subject to the old fallacy of assuming the cause. I still think we're going to have to do it. Reactive power and apparent power and all of these things are not different flavors of power. They're actually none of them power, except the only thing that's power is the instantaneous power, and what we call power is actually the average power. Meaningful reactive power measurement is possible, sort of, maybe, provided the distortion isn't too much. Just use the fundamental. And apparent power and power factor are beyond rescue. They are over there in legal metrology territory, so we should throw them out. Power theories are failed attempts to explain measurement problems. Doesn't work. And reactive power is just the oldest power theory, and it's very familiar. It's still nonsense. Hard to say. Everything we know about a power system comes from measurements. We did not evolve anything about our senses that will let us sense electrical magnetic fields. And we talk about digital twins. Fine idea, but not using the sort of modeling we're doing now. I think we need a digital twin to base itself only on the observable quantities and solve these systems as network problems, not power system problems. Next. And we've touched on the surface of measurement theory here. It can teach us a great deal more. I got started in this business of measurements at this level of depth because I was involved in the IEEE standard for the phasor measurement unit. So I could criticize it. I was there. I am partly responsible for what a disaster it is. It's hard to understand unless you understand some measurement theory, but the business of the phasor measurement unit could be the best measurement in the power system. It is probably the worst, and it doesn't need to be. Several people have made much better PMUs than would comply with the standards. And I'm one of them, but one of my colleagues, as the guy in Ireland, has also done that. Next. Yeah, is that you? If you would like a talk on just the PMU, ask me. I'm perfectly happy to do that. Next. Are there questions? I'm not seeing anything in the way of a question. So are there any questions? I'll put my camera back on, although I should be able to hear you soon. Oh,
Yeah,
let me scroll down a couple. There's a list of the citations if anybody wants to take a picture of that. Keep going. There. Okay. Are there any questions?
Yeah, first of all, yeah. Thank you, Harold. That was very engaging talk. So let's just start the questions. So people online, if you have question, please unmute yourself and ask your question. Any question from online audience? No? Okay, we can come back to you guys. Okay, people in the room. So. Yeah, you have some questions.
I do.
Yeah.
Thank you for.
I become expert on identifying who has a question.
All right. I mean, it's not. I haven't studied measurement theory, but it was a good expose and it's interesting. But when you say like power theories are wrong, like how everything else is working, like why are we getting power from? Like how is this infrastructure working if the power theory is wrong?
I'm having some difficulty understanding exactly what you said, but the question seemed to be, how can I say power theories are wrong? Because power theory as defined as a way to explain the difference between P and S are all wrong. There is no question about that. When we talk about analyzing a power system and look at the power flow, do a load flow, that's a different question. That's not a power theory.
Okay, and but then there is we do, I think, Q control for synchronous machines and stuff. like that should hold some notion, right? Like there is some physical, like the way I understand it, it's just some energy fluctuating from between, like let's say, magnetic energy, right? And as the flux, and that is associated with your Q. So why
No,
is that thing?
no, 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 no. You are making an assumption. If the appearance of Q might be stored energy oscillating, it might be displacement caused by distortion, it might be the presence of some harmonics. From the measurement, you cannot distinguish it. And that's the point. What we have done after 1901, we started to believe that reactive power was something real. And it isn't. It's only the result of a measurement. The only things real in this system are the voltage and the current. You can observe them. And reactive power is based on an assumed relationship between the mathematical functions describing the voltage and the current. And we have not thought about the conceptualization of reactive power beyond the 1901 version.
Okay, that makes,
Yeah.
So if you remember the random number diagram with colored dots all over it, that's reactive power. It depends on how you measure it, what you get. Did you know that? There's no such thing as reactive power, but if I do make this measurement, I do this, and I call it reactive power. That's a mistake. If I use a different method of measurement, I get a different result, and I still call it reactive power because I keep making this mistake. If I measure octane by the R method and octane by the M method, I label them R and M, and they are not the same number, and I don't take them to be the same thing.
okay, that makes sense. Is there any place that you can go and read about this? Like, do you have a power theory which is consistent with what you say?
I do not have a power theory. All power theories are wrong.
Okay.
Our book is expected to be published. I spoke to the publisher at the general meeting of PES and said, when is it going to come out? Because about the time of the general meeting was when I was sending the manuscript to them. And the answer was, it takes a few months, probably this year. So by the end of this year, we will probably have the book on the market. I don't know exactly how big it's going to be. I know how on my draft how big it is, but I dare say they will be printing it in a different format. So, but it's a big book, and it takes until the 5th chapter before we encounter power theories.
All right, that sounds.
What you've had this day is a very rapid, accelerated version, especially since we started about 10 minutes late. A very rapid version of the first 4 chapters before we get into the business of reactive power theories. And I got to say, it took us a few years to figure it out. So, you know, it's okay to be going, is that right? Still.
Yeah, I think I'm good. Thank you for answering my question.
Okay.
Yeah, Harold, I think maybe if we want to a little bit elaborate on his question, maybe what he's saying that we have the actual physics of the power grid, and somehow magically people come up with set of equation. But then using those equations, which are, as you have discussed, that they are not correctly describing the physics, but it's still using those wrong equations, they can operate power system.
Well, so the deal is, you know, you solve the power load flow by a program like PSLF, and PSLF draws on work done by Brian Stott and Angun Alsach back in the early 70s, in which they decoupled the power solution and the reactive power solution. And since then, everybody's been doing that. and you add a few more features. PSLF was written by a company owned by a couple of friends of mine, John Undrill and Roger Clayton. So I sort of know the inside story of a bit of that. And the assumption is that the distortion on the network you're analyzing by PSLF is less than 1%, because you don't treat the harmonics at all. And you get an okay answer. But here's the problem. At PNL, I was asked dozens of times by one particular guy who was an expert at running PSLF. And he came to ask me many times, what about drift in current transformers? To which the only answer I can give is current transformers don't drift. You know, it's a piece of iron and some copper, and unless you can unwrap a turn somewhere, that you got the number you're going to expect. And he says, but I can not always get a good convergence on reactive power in PSLF. Well, the reason you can't get convergence in PLSF is the bloody reactive power measurement sucks, because you've got the random number effect going on. Power is more or less power. There isn't a lot of power in harmonics in the transmission system, but the reactive power is a real bugger, and it does depend on slight 2% distortion will give you a 2% wrong answer and will screw up your convergence.
So therefore, can we say that they can somehow use that one because we don't have that much harmonic in the system compared to the fundamental frequency?
I think that the best way to proceed is to stop looking for simple answers until you know that they exist. So you need to understand your power system in real time. Now, there are ways to do that. They're also described in the book. You never see a statement in the electric power system as such and such power plus or minus 2%. You don't see that sort of declaration of noise effect or uncertainty or whatever it is. We just don't do that. We need to get in the habit of doing that. Now, it turns out you cannot put an uncertainty number on an operational measurement. It doesn't apply. You cannot. One of the things in that big table comparing operational representation, well, you cannot trace an operational result back to something at the, as it were, at the national laboratory or like that. So what do? What you can do is assess in real time what's the distortion of your system. And there are interesting ways to do that are described in the book, that describe how you can generate a number that's very much like an uncertainty number, given that you've got the real shape of the voltage that you're looking at, and you know, because you've got maybe a PMU on it, or you can analyze it, you can describe exactly the sort of effective uncertainty caused by that distortion. That's doable in real time. It's a simple calculation, it turns out.
Thank you. Yeah, that's clear up everything. Yeah.
I have a question. So, yeah, if I understood correctly, you mentioned that it's good to use the fundamental components for calculation of reactive power in case we need to use them for controls. Am I right?
I'm not understanding you. You may be far from the microphone, or I don't know, but
okay. So can you hear me?
Yes.
So if I understood you correctly, you said that in case we need to measure the reactive power, we should use the fundamental components of voltage and current without considering the harmonics.
Yes.
So do you suggest to use the same approach even for control designs where we want to control the reactive power flowing through different parts of the network?
Frankly, yeah, but I think there's a problem with controlling reactive power. What you really should do is look at the voltage and see what you want to do, and maybe crank up the excitation on a generator is one possibility, or throw in some capacitors is another. But the question is really a question of voltage, not reactive power. And if you look at what's going on in some DC fed sources like wind turbines, there are serious problems that I think come from the attempt in the inverter-based source to control reactive power, or that is to say, to control the switching of the rectifier elements according to reactive power. Because if that gets slightly, if the signals get slightly distorted, your reading of reactive power will be just bizarre. And you will send that signal coming from your reactive power instrument into the control loop, and you will screw up the bloody control loop. Now, in my history, I've made inverters, I've made AC-DC converters in the past. And probably the best thing to do if you get a severe disturbance on the system is just clamp all the control values until it's gone. Because while current is going off, if there's a fault somewhere on the system, it doesn't have to be close, but if there's a fault somewhere on the system that distorts the voltage, it will screw up all your readings. I mean, so the goal surely is to ultimately protect the inverter itself. So you've got to keep all the silicon or silicon carbide or whatever they are these days in its safe operating region. That you cannot let go of, but you can afford to clamp some of the control signals for a couple of cycles without any harm, I think.
So similarly for active power calculation, so do you suggest, how do you suggest that we should do the active power calculation? Suppose we just have the voltage and current readings or measurements available.
Where are you doing it is part of the answer. So all measurements are made for some specific purpose. Now, if you've got a case, somebody gives you some data in a university test, I don't know what you would do. Probably make the assumption that it's all sinusoidal stuff. But if you're out in the real world trying to control reactive power because you're getting low on voltage somewhere, how do you control reactive power?
So yeah, I'm thinking on the sense of a power plant operator, where I'm supposed to supply required or the asked amount of power to the grid. So in that case, the harmonics can have significant amount of power, and I might push more or less than what I'm asked for because of the harmonics. So
yeah, harmonic power is. The reality is that generation doesn't produce harmonic power. It produces sine wave power, and load converts a lot of it to harmonic power. And it turns out if you monitor a load carefully, depending on what the load is, you can find a situation where some loads generate power at harmonics by taking it from the power system at fundamental and reflecting it back at harmonics. Some do the opposite. They take power in at harmonics because it's already on the system and can use it in their control of whatever their load is. But a lot of loads, a lot of large solid state controlled loads have either an electric bill which is larger than their power consumption or lower, depending on how you look at it. It's strange. You don't think of this with power, but it's just as true with power as it is with reactive. It's being measured as an average, and you build on an average power. That's average over some number of cycles in the short term. It's average over some number of minutes in the long term. But it averages out all the harmonics. And if the harmonic power is flowing in one direction, you get an addition. If it's flowing in the other direction, you get a subtraction. And you forget that you've just taken the average of all of that. It's strange.
Yeah.
And when you get a fault, goodness knows, it's a real challenge. Try the experiment. If you've got some fault data, try the experiment of trying to calculate power and reactive power out of one voltage, single phase, one voltage, one current through a fault. And then you stand back and ask yourself, does this mean anything?
Okay, yeah, I think, okay, we might be over time, but yeah, I think when we have a number of harmonics and when we try to calculate reactive power, yeah, it can give crazy results. I've tried that. Yeah, thank you. Really interesting presentation.
Thank you. If anybody wants to write to me, Professor Lofifard, now sure, we can circulate my email. That's okay.
So any more questions? No? Oh, you have, yeah, go ahead. Sure.
Thanks, Harold, for the nice presentation. I don't know if you have time to stay a bit longer or you want to step out, but I really enjoyed your presentation. Maybe we can have hours of discussion on these topics because I'm really interested. But I have some questions. I don't know if you have time to answer any of them. So the thing that came up, I have also looked at some of these standards that you mentioned. I also acknowledge that there are different ways of measuring active or reactive power, and also there are also different definitions for these active power, reactive power, and even for apparent power. For example, we have arithmetic apparent power, things like that. And things become really complicated when we also involve harmonics in the system. So that example that you gave for those random generators, that you had a sine wave and the other voltage or current was distorted, and you mentioned that there can be a phase displacement. And then you mentioned it would be better to measure reactive power only considering the fundamental components and multiplying by the sine of the phase displacement. So my question to you is, what if the phase displacement is zero? For example, in many of the circuits, for example, if you have a diode bridge, your voltage will be in phase with the fundamental frequency of the current, but the current would still be distorted. So in that case, if you only consider fundamental frequency, then the reactive power will be equal to zero. But how would you then explain that active power will not be equal to apparent power? Understand that philosophically.
Well, let me answer right away. The fundamental answer is there is no reason to think that active power and apparent power should be equal.
Should be equal, yeah.
That is just an assumption based on nonsense, and the nonsense is the power triangle. And the power triangle is based on reactive power, which is nonsense. So it's a closed loop of answering a question that is nonsense with further nonsense. Why should these things be equal? If you write out the mathematics of apparent power and the mathematics of average power, the only way you can make them equal is by a substitution so that you can map one into the other as a resistive load. That's it. There's no other solution to that.
Yeah, let's say even that you have connected a resistive load. So let's say that you have a voltage source, a single phase voltage source, connected to a diode bridge, and then the load at the DC side is a pure resistor. So now the power that you're delivering to the resistor is that active power, and then let's also assume that there are no losses in the diode bridge. But the apparent power, I understand that philosophically engineers try to make up something called reactive power so that they make an equation that apparent power somehow is a function of active power and reactive power. But if reactive power is zero, and you only consume active power in that resistor, then
the thing is, apparent power is legal metrology. And if you look at the country of India, and you look at what the different states have allowed in their measurements, 10 of those states allow apparent power to be used for billing. Now, they're perfectly entitled to do that because this is legal metrology. but they are experiencing problems because it is bloody nonsense as well. And the idea of apparent power is one that has no real merit. It's very handy and it works on a single phase system to have some slight meaning, the product of the RMS value of this and the RMS value of that. But RMS is itself an operational measurement. You lose all information about distortion, phase, anything when you get the RMS value. You don't know if it's a sine wave, a square wave, or triangle wave, or whatever it is. And you take that twice and multiply it together. Once you start digging that deep, you should stop digging. You're in a hole. Apparent power is a problem. Reactive power is a problem. Power factor is a problem. These things deserve to be left to the people in legal metrology who deal with this magic where this car has a 2 horsepower engine and so on. And scientists, and I hope to think that we might call ourselves engineers, but we think like scientists, we don't attach much significance or meaning to the nonsense of reactive power, apparent power, and the power triangle. I know I'm undoing 100 years of nonsense because the power triangle came into being about 1910. And it was bloody useless by 1927. Otherwise, Budano wouldn't have written his book. But we don't give it up. We hang on like it's a religion, and it's not a religion.
Okay, and what is the current approach to calculate reactive power in industry? Do you use the Budano's definition, or what definition do they use to?
Budano is, I'll tell you why Budano is nonsense as well. I mean, when you read the book, you have to read the book in French. When you read it, you find there's a statement on page 210 that can only be interpreted to mean that distortion power moves in a wire without producing an electric field or a magnetic field. Now, you know it's nonsense right away. And it turns out this is buried on page 210 of a book written in French, and it looks to me like not enough people read the original in French and got that far before they saw it. But I discussed this with a guy called Alex Emanuel. Alex Emanuel, excuse me, was the previous chair of this committee, subcommittee that I'm chairing, rewriting Standard 1459. And he was educated by Budano, and he believed everything Budano said. And I flew over to talk to him over in Massachusetts. He's at Worcester Polytechnic. And we spent a day talking about this. He speaks French, I speak French. We both had a PDF of the book. And we spent a day talking about it. In the end, he had to agree this was a mistake. It wasn't the only mistake we encountered. And we wrote a paper saying what nonsense it was, even though he had put this into the previous edition of Standard 1459. So distortion power, it should be obvious. You can't calculate it. You can only calculate distortion power assuming that you already know reactive power. And you can only calculate reactive power, according to most people, assuming the power triangle is true. So there's some serious problems, and they are not power problems, they're measurement problems. The network theory stuff is perfectly valid. And I think what we have to do is go back to looking at our networks and solving them as networks, not taking all these shortcuts. We have the computer power to do it these days.
Thank you.
Yeah, Harold, thank you very much for such a interesting and engaging talk. So usually in the class, I try to challenge the student. I call it fundamental question, but you made the existential questions to them. So let's plan.
Yeah.
Yeah, let's plan to have another talk maybe on PMU, sometimes end of this semester or next semester.
Yeah. Somebody called Menuka has asked me to explain more about the PMU, and I've suggested that that person write to me because there's no time to talk about it here. But yes, I'm perfectly willing to talk about the PMU, and I think I've tried to persuade somebody from NASPE to get involved, because NASPE contains all the mistakes, and that's a shame, because NASPE is a valuable entity. I think it just needs to get cleaned up.
Oh yeah. Actually, you answered the question in the chat. Yeah. So yeah, sure. So I will follow up on the PMU talk. You will find sometimes that fits your schedule. Okay. Thank you very much.
You're very welcome. Thank you.
Yeah. Thank you. Have a good day. Bye.
Yeah, you too.